right? From the three equipment that I talked to you already, like the filtration, centrifugation, and cell disruption. After you separate the solid from liquid, if you product in the liquid, the next step you have to separate or increase the concentration of product in the liquid phase. The one technique that we commonly use to purify or to separate the product or to concentrate the product concentration is the extraction. Extraction. We have both solid liquid extraction or liquid extraction. That's like for the liquid extraction, that means we have a mixture of solute in the liquid. That's like both solvent and solute, many solvent. That's like, and then you have to separate the solute. You have to use the liquid solvent. That's like to separate the solute. And solid liquid extraction, that means the solid, we would like to extract some chemical or some molecule from the solid. You have to use the liquid solvent to extract the chemical from the solid, like this. For example, if you would like to separate the volatile organic chemical from the solid compound, or like from the fruit, from orange juice, from the many kind of the solid that in bioprocess, things like this. But for this, I will talk in the liquid extraction. That's like liquid extraction. For that case, we use liquid solvent to extract the solute from the liquid mixture. We call it a solution. That's right. Most completely, the solution contains two components: solute and solvent. That's right. Solute and solvent. And then you add the another component at the liquid solvent. That's mean if you add the third component with this solvent should be dissolved in the solute, and the solubility is higher than the solvent. That's right. We have two solvents: the old solvent that mixed with the solute, and a new solvent. That means the new solvent should be higher dissolved in the solute. That's right. And then the solute will transfer or move from the old solvent to the new solvent. This is the technique. This is the basic technique. Okay, the extraction process take an advance of the partitioning. Partitioning means separate. That's right. Of the solute between immiscible liquid phase. Immiscible liquid phase, that means the liquid phase cannot dissolve. That's why we can separate the liquid phase between two sections or two parts. That's why sometimes the lighter liquid and heavier liquid. After you mix together, and then these two liquids will separate. The lighter one is at the top, the heavy one is at the bottom. That's why we can separate this by the density of liquid, something like this. Okay, for example, like penicillin can dissolve more rapidly in amino acetate than water. That means from the production of penicillin. Penicillin dissolved in water. That's right. For example, if we operate at pH 5.5, if you would like to separate penicillin from water, you add amino acetate. That's right. Because amino acetate dissolved penicillin is higher than water. This, for example. And also with citric acid is more soluble in methyl amine ketone than water. That's why that means you make the methyl amine ketone to separate citric acid from water at pH 4. That's right. This is the example how to select the solvent to separate the solute from the unsolvent. That's right. Okay, from these two examples, each concentration or solute concentration increased in the first liquid phase as a result of depletion from the second phase. Like from the solute transform or transfer from the first phase to the second phase, something like this. So, okay. For this case, we use the term of partition coefficient K. That's like K is equal to X divided by Y. That's like for this case, we consider it for the tank, something like this. We have tank, we have the liquid. This is L and S. L is lighter liquid, S is heavier liquid. When you mix this together, that's right, mix together, And then the liquid phase will separate into layer, the top and bottom. The bottom should be heavier phase. The bottom or the top, it should be lighter phase. It's different in density. That's right. Okay, we represent X is the solute concentration in the lighter phase, or L. That's right. In this phase, we have the X and Y. That's right. Y is the solute concentration is the heavier phase. This is the definition. In many cases, light phase will be on organic solvent, or heavy phase is water. Most in bioprocess, the heavy phase is water, because after you fermentation, that's right. After the fermentation, most component is water. That's right. Most component is water, and K is a constant with independent of solute concentration, but it depends on the solvent phase. Solvent pair. It may be methyl acetate and water. This may be ketone and water, something like this. In the bioprocess, we have 3 systems for the extraction solvent. We use the aqueous, non-aqueous, organic aqueous two-phase, and supercritical extraction. That means we have the organic solvent and water. Aqueous means the solution that the water is the solvent. That's right. Aqueous, non-aqueous, or aqueous solvent is the first system. And the second system, aqueous two-phase. What does it mean? That the origin solution is water and solute. And also the second system should be water and the solvent. That's right. Both phases have water. And the last one is supercritical fluid extraction. That's right, supercritical fluid extraction. For the ideal operation, the liquid extraction do not react with solute. That's right, not react with solute, and non-denaturing, non-toxic, inexpensive, immiscible with the feed. That's right, and also provide a large coefficient or distribution coefficient, large K value. It's higher K value. It's higher separation efficiency. That's right. And also the important is the different in density. That's a high different in density. Interfacial tension should be low enough. That's right. This is low enough to it's easy to contact between the phase. That's right. It should be high enough and low enough, something like this. Okay, for the case of low density different or emulsion of it, sometimes you have to use the centrifugal extractor. Like centrifugal extractor, you have both technique, the extraction with solvent, and also use the centrifugal force to increase the efficiency of the extraction. For the case of low density difference between heavy phase and light phase. Yes. This is gives you conclusion about the disadvantage and advantage of the 3 types of the liquid extraction. Aside the first, we talk about aqueous, non-aqueous. Aqueous mean like solute plus this solute plus water. This is the origin solution, and then you add some organic solvent. That's right. This is the first system. This is aqueous solution. This is non-aqueous solution. This is for the first system. And the second system with aqueous two-phase is solute plus water. And also the second is solvent plus water. That's right. We have water in both phase. We call it the aqueous two-phase extraction. It's the most common used for the bioprocess. For this case, we solve the problem that some solvent will denature the protein, denature the biomolecule. We use the aqueous two-phase. And the last one, we use the supercritical fluid extraction. Okay. The advantage or the aqueous, non-aqueous is maybe like the pure crystal obtained, and also the solvent, pressure of solvent is higher than pressure of water. Evaporation of water for water is greater than solvent, and also sometimes organic salt remain in the water. This is we apply for the carboxylic acid to separate amino acid, alcohol, steroids, something. This is example of the solute that we would like to extract from the aqueous system. And there are also some disadvantage for this system. That's right. some biopolymer denatured by organic solvent, because the organic solvent some denature or some toxic to biomolecule. That's right, especially for the biopolymer like protein, polysaccharide, something like this. And also we use the organic solvent. The cost is high or expensive. That's right. Some organic solvent is toxic. Some permeability. That's right. Permeability. And also we have to manage the waste disposal because it's organic solvent. That's right. We have to manage or treat the water after some treatment. Okay, the next it is the aqueous to phase. Mostly we use for separate protein, enzyme, virus. That's right. For the example, like organelle cell, something like this. The aqueous to phase, it is friendly for the biomolecule. There is no toxic. That's right. It's low toxic when compared to the organic solvent. And also they can preserve the activity of biopolymer, like enzyme, like protein. This is the biopolymer. That's right. And also for this, it eliminates the disadvantage of organic solvent. That's right. But there are some disadvantages. For example, pure lactane polymer is quite expensive. That's right. It's some small phase density. Sometimes if you use the aqueous to phase, the density of both phase is quite small, different. That it is difficult to operate. That's right. It's difficult to operate. And the last technique, we use the supercritical phase extraction. Supercritical phase extraction. Mostly we use for separate alkaloid, that's like biopharmaceutical, that's like alkaloid, like therapeutic foods, beverage processing. That's right. For this case, its advantage is for example, solid penetration or use dissolution it is. And also CO2 solvent, inoculate is it non-toxic, that's right. And also it is easy to remove, but also disadvantage for high cost for supercritical phase extraction, high pressure equipment, that's right, high compression force. And also we need the experimental to determine the condition that appropriate for the application. This is the disadvantage and advantage of the three types of the liquid extraction, like aqueous, non-aqueous, aqueous to phase, and supercritical phase extraction. I will show you all of this in this class. And also for this table, show you the K value. K value is the partition coefficient. If K value is high, it's high separation. That's right, high separation. If K value is high separation, because K value is the ratio of the concentration in the light phase divided the concentration in the heavy phase. If its concentration in the light phase is higher than heavy phase, that means we can separate the solute from the heavy phase to the light phase. Now, for example, if you would like to separate alcohol like ethanol, butanol by N-octanol at the solvent at temperature is 25, K is around 0.4. If you butanol is about 7.6, it's easy to separate butanol by octanol at 25 Celsius. But it's difficult to separate ethanol by octanol, which for example. Right. And for another example, right, to amino acid glycine, alanine. If you use the organic solvent, I think the K value is very low compared to this. Is quite low, right? It's difficult to separate amino acid by butanol, for example. Like by butanol, for example, your K value is low. And another example, that's right. If you use the butyl acetate to separate novel biosyn, K value is very high at pH equal to 7, but P value is very low at pH 10, quite far. That means temperature also affect and pH also affect the extraction system. Right. This is because you can compare. This is for amino acetate to separate erythromycin. That's right. At 6, K is 120. At 10, K is very, very low. That means pH is effect to the separation. So I need to show you the K value of the system. That's right. What kind of solvent and what kind of bioproduct that you can separate by extraction using the organic solvent. It depends on temperature. It depends on pH. This means by K value. That's right. Or K value. Again, K value is defined as the concentration of solute in the light phase divided by solute in the heavy phase. If we recall the chemical potential in the theory of chemistry, so the K is based on chemical potential at equilibrium. That's right. K for the heavy phase and K for the light phase. We express in terms of chemical potential for heavy phase and light phase. And also we can express in terms of chemical potential at standard state. That's right. Plus RT log Y equal to at standard state. It is in heavy phase, this is in light phase. That's right. And also you can calculate K equal to X over Y in terms of chemical potential. That is equal to exponential of chemical potential at standard state of heavy phase minus chemical potential of standard state at light phase divided by R. That you can express the K in terms of chemical potential by this equation. That's right. And also this is show the K in terms of solubility parameter. That's right. Solubility parameter. Solubility means the amount of solute that can dissolve in the solvent. That's right. Maximum amount of solute that can dissolve in the solvent at constant pressure and temperature. That's right. At constant temperature and pressure. Okay. You can express K in terms of the solubility parameter and the molar volume of the substance of the heavy phase and light phase. That's right, heavy phase and light phase. And this table shows the data of solubility parameter. It's delta for any solvent in liquid. That's the case. Higher parameter is higher solution, higher solubility. Again, the solubility is the maximum amount of solute that can be dissolved in the solvent. This should be at constant temperature and pressure. We have to specify what the temperature, what is the pressure that you talk about the solubility. It's very important solubility to design the extraction system. As a higher solubility. For example, if you would like to separate the alcohol from the water alcohol mixture, then you need to choose another solvent that can dissolve or the higher solubility in the solute than water. This is very important. That's very important. Okay, and also the separation based on extraction also it depends on the ion pair, because in the bioprocess there are some electrolyte solution, protein, amino acid. Also, when you dissolve in water, it may be ionized. That's right, ionized to negative charge, positive charge, something like this. Okay, for the organic partitioning of cation, anion, or switcher ion. Cation is the positive charge and it's negative charge. For switcher ion, the net charge is 0. That's right. That means the compound can ionize into positive and negative charge for switcher ion. Okay. The ideal ion pair agent are water, soluble when ionized. Hydrophobic. Hydrophobic means don't like water. That's right. Like water. When paired to the hydrate, it easily to dissociate with return to the desired species. That's right. And the next counter ions from organic soluble salt, for example, are common ion pair for the extraction. That's right. That means the organic salt should be the common extraction or common extract. That's right. Solvent. Acetate or butyrate. That's right. Acetate or butyrate. It's also organic solubility exceed that of the acetate. That's right. Ion pair for cationic biopolymer. That's right. Biopolymer. This for example that we use the ion pair technique, because when some solution dissolved in water, it may be ionized to the cation, ionized to the anion, ionized to the positive charge, ionized to the negative charge, or it's ionized into the two charge, negative and positive. That's right, with the ion. Like for example, right, we would like to take the butyl ammonium cation pair, that's like with chloride anion, and then we compare to this electrolyte in chloroform in light phase, water in heavy phase. For this system, we use the chloroform at the light phase or the solvent. When we dissolve this together, the yield of the K partition coefficient is maybe the ratio of the ionic chain ion pair of the cation in chloroform, and also cation in water is about 1.3. Okay, if we add some another, we add some sodium acetate. That's right, sodium acetate in chloride solution. As for this case, we will increase the K value. In the K value, it also is depend on the type of salt. That's right. For this case, we use chloride ion. But for this case, we use the sodium acetate. These two salts. When you add the chloride, the K value is 1.3. When you use the sodium acetate, the K value is 133. It's higher. That you eat. If you use the sodium acetate, it's easy to separate when you use the chloride. That's right, chloride and ion, sodium chloride, something like this. This also depends on the ion pair that you add at the solvent. That's right. Okay, for this table, show you typical counter and for ion pair as acetate. Like this. This is butyrate. That's right. And another, this is for example, for the organic solvent, that's also the ionite in the solution in negative charge or positive charge. This is for acetate is negative. Butyrate is negative. Butyl ammonium is positive, for example. Like for this case, in when you replace the sodium acetate instead of the chloride ion, the K value is increased. That means the separation by affection is increased with you change the salt. That's right. And also the solution is depend on the type of the solvent, and also it depends on the pH. That's right. If the pH change, attraction change based on the K value is changed. Also, as I showed you previously in this table, like in this table, at different pH. That's right. 4 and 6 is also the same, right? The same organic solvent, but different pH. K value is changed. That's right. This means the K value is depend on the type of pH. That's right. The value of pH. Okay, when you ionize some solution, when the solution is ionized, K value is depend on the like this is maybe some weak acid and weak basic system. That's right, weak acid and weak acid or weak base system. That's right. Also, when you dissolve weak acid solution or weak base solution, there are some the negative and positive charge. That's right. Okay, the apparent partition coefficient can be shown by this example. That's right. And also for the acid, as I form the ionized in water, we can is the negative and positive charge. And then Ka is equal to product divided by the reactant, the concentration. That's right. The multiplication of concentration of product divided by the reactant. This is the Ka value. And then you can calculate K, this partition coefficient, equal to Ki divided by 1 plus Ka. This is term of Ka, or Ka. And then you can group it in this log Ki divided by K minus 1 equal to Ps minus Pka. Pka is the association constant. That's an associated constant based on the solution on the compound. That's ionized into negative and positive charge. Like for the pKa of the weak acid, pKb should be the weak base. That's right. We have two. Ka for the weak acid, Kb for the weak base. So you can use this formula to equate the effect of pH and pKa to the K value. That's right, to the K value. And also you can use compare to system by the selectivity. For this case, selectivity of A and B. If the selectivity is high, that means you can separate A easier. If B is low, it's difficult to separate A and B for that case. That's if the beta equal to 1, okay, it cannot separate. If beta is greater than 1, you can separate A from the mixture of A and B, for example, like this. I did show you some parameter that's like for pKa of any compound, mostly pKa for the acetic acid, propanoic acid, we only pKa. This for weak acid. And also we have some pKa of amino acid, because amino acid can ionize into 3 groups. That's it's carboxylic group, amino group, and also a group. It may be 3, pK1, pK2, and pKt. Because amino acid is the compound that is include about the chemical group at least 2, and some compound is 3 group. That's that. 3 group. Okay. I will talk to you about the example of the how to calculate K, how to use the K to predict the efficiency of the extraction for the next week. That's right. Okay, I would like to stop the lecture for today.